Let's do an example. So in this example, we're going to consider a double integrator system. And a double integrator system is given by these dynamics. So x1 is equal to x1 dot is equal to x2, and x2 dot is equal to your input. Okay, and then we're only going to be able to measure, let's say, the position, or x1. Double integrator systems are pretty nice since a lot of physical systems tend to follow a double integrator due to Newton's laws. So acceleration is equal to some function of your positions and velocities and other perturbations and whatnot. But so double integrator system is really useful to learn in practice because a lot of systems end up reducing to some form of a double integrator system. So the goal of this is to design a proportional feedback controller and a state observer such that the following characteristic equations hold. So again, we're going to be using a state observer-based feedback controller, similar to the one I presented, well, as I presented in the previous lectures in this lesson. And so we want the observer and the controller to satisfy certain properties. Namely, we want the observer to satisfy a characteristic equation equal to s plus 10 squared. So that would basically be putting our eigenvalues of our observer at -10, which means that will converge exponentially fast, e to the -10-ish times t. And we want like I mentioned before, we want the controller to converge slower than the estimate. So we want to make sure that we're not converging to a place where our state's not. So that's why we want the observer to converge faster than the controller. So we're going to have the controller satisfy we want to pick our controller gain such that our system satisfies s plus 4 squared. So it's putting our eigenvalues at -4. Okay, so we'll have a stable controller, but it's slower than our observer. So what do we do first? Well, let's make sure that our systems are controllable and observable. Okay, so to do that, let's look at our various matrices. So our observability matrix, O bar, is equal to C and C times A. Okay, so if we look back up at our system here, C is 1, 0. So let's plug that in. Equal to 1, 0. And C times A, so if we have A right here and C right here, let's make a little box over here. Great. Okay, so C times A, this is equal to 1, 0 times 0, 1, 0, 0. Okay, so this is equal to 0 and 1. All right, so let's go back here. 0, 1. What's the rank of this observability matrix? Right, 2. Rank of O bar is equal to 2. Why is that? Well, if you look at this matrix, these two either row vectors or column vectors are obviously linearly independent, right? You can also look at it by looking at the determinant of this matrix. So the determinant of O bar is equal to 1, which is not 0. So that means that none of our row or column vectors are linearly dependent on another one. That's another simple way to check. Let's look at the controllability matrix, C bar. So this is equal to B and then AB. If you come back up to the system, B is equal to a column vector, 0, 1. So this will be equal to 0, 1. And then A times B, let's just go back over here to our side. And so we get, oops, yeah, so 0, 1, 0, 0, and B is 0, 1. Right? So this is equal to another column vector, where we get 1 and 0. Right? So this is 1 and 0. And now what is the rank of this guy, of our controllability matrix? Oops. 2, right? And again, we can look at the determinant of C bar, and this guy is equal to -1, which again is not equal to 0, which means that we can, that the rank of our matrix is equal to the dimension. Great, so now we have our controllability matrix, we have our observability matrix, we have the characteristic equations that we wanted to satisfy. Now we need to choose our gains. So we can use Ackermann's formula that I presented previously. Okay, so let's look at the estimation, the observer design first. So observer design. All right, so the Ackermann's formula is L is equal to alpha A times O bar inverted times 0, 1. Okay, so the characteristic equation that we wanted for our observer is S plus 10 squared. Okay. So if we come back down here, let's go. This guy is equal to S plus A plus 10I squared times O bar inverse times 0, 1. All right, so this will be A squared plus 20A plus 100 times I. Okay, and then we'll have that our inverse of O is just the identity, so this will be 1, 0, 0, 1, and then 0, 1. Great. So A is equal to, let's come back over here. A is equal to 0, 1, 0, 0, which means A squared is equal to 0, 1, 0, 0 times 0, 1, 0, 0, which is equal to, running out of room. Okay, so this guy is equal to 0. This one is equal to 0, 0, 0. Great, so let's come back up here. So A squared is equal to 0. So 0 plus 20 times I plus 100 times I times 0, 1. Oh, this is not I. This is 0, 1, 0, 0. All right, so now let's go over. So this means that we have 100, 20, 0, and 100 times 0, 1. which means that we get L is equal to, erase that guy, L is equal to, we do this out, this will be 20, and then 100. So now we have a gain for our observer. Okay, so now what about the gain for our controller? So now let's look at the controller Ackermann's formula. Right? Okay, so we wanted this guy to satisfy this characteristic equation. Alpha of s is equal to s to the 4th squared, which is equal to s squared plus eight s plus 16. Okay. All right, and then the Ackermann's formula is equal to k. This will be 0, 1, this matrix on the left side. Again, it's all zeros, and then the last element's equal to 1. Our controllability matrix, inverted, and then times the characteristic equation of A, and when we input A into it. All right, so now let's do this. So this will be 0, 1. C inverse is equal to, so this will be equal to, this will be 0, 0, 1, 1, inverted. And then alpha will be A squared plus S8 times A plus 16I. All right, so now let's do this. Let's go, this will be 0, 1. The inverse of this matrix, the controllability matrix, is equal to, I believe it's negative 1, 0, 0, negative 1. Let's make sure. Zero, 1, 1, 0. I'm just plugging it into MATLAB. Great. Not negatives. Just itself. 0, 1, 1, 0. And then we know that A squared is equal to 0, right? And then we get 8 times 0, 1, 0, 0 matrix plus 16 times 1, 0, 0, 1. Let's make that a parentheses. Cool. All right, so next. This guy is the left-hand side matrices multiplied together is equal to 1 and 0. And then this guy will be a matrix with 16 here, 8, 0, and 16. Right, so I just did the sum. And then this guy is going to be equal to 16 and 8. So then at the end of the day, we'll get K is equal to 16 and 8. All right. So now let's see if we can simulate this. All right, got MATLAB up. So let's type in, oops, click on that. Let's type in our matrices here. So A is equal to 0, 1, 0, 0. B is equal to 0, 1, C is equal to 1, 0. L is equal to 20 and 100 vertically. K is equal to 16 and 8. Great. So what we can do, this is going to be the combined observer and controller design that I presented in the first of this series of lectures. So we're going to look at the full system here. So I'm just going to call this tilde A matrix. And this tilde A matrix is going to be equal to A minus BK, B times K, B times K here, 0, and then A, let's do zeros, and then 2, which is going to be a 2 by 2 matrix full of zeros, and then A minus L times C. All right, so that gives us this matrix here. And then, so what we want to do is we want to look at simulating this using ODE45. So what I'm going to do is I'm going to create a function called my function, an anonymous function. This is going to be equal to at t and a tilde x, where tilde x is the error component of our system and the state of our system, with the state being the first element and this error being the second element. And so then this will be tilde a times tilde x. Okay. Great. So now what we want to do is we want to look at ODE45. So ODE45, and then we want to use the function myFun, right? And when we want to simulate it, let's simulate it from 0 to 10 seconds with initial conditions randomly chosen. Let's do 5 times rand of a vector of 4 or 1. Okay, so this will be randomly chosen initial conditions anywhere between 0 and 5. So let's run this and let's see what we got. Okay, so this is what we're looking at now. Let's see what let's look at a legend. Let's just label everything so we know what colors are what. E1 and E2. Great. Okay, so that should pop up with a legend here. Make this a little bit bigger. Okay, so let's see. So what are we looking at here? We've got x1 and x2, e1 and e2. We can see that e1 and e2 they converge much faster than x1 and x2, right? So we designed our system such that our observer states will converge to that observer states will converge to the state of our system much faster than our system will converge to the origin. And we can see that here, right? We can see that we have the error E1 and E2, and they're converging to 0, which means that the estimate is converging to the state of our system. And then we have the blue and the red trajectories here converging to the origin at a slower rate than the estimate, and that ensures that they're actually converging to the state, to the estimate, which is equal to the or they're using the estimate, which is converging to the state, to converge to the origin. Whereas if the estimate was slower than the system, the state would converge to the estimate, but the estimate's not going to converge, but not necessarily to the origin. And so it's best practice to have a significant difference between the eigenvalues of your observer and the eigenvalues of your controller to ensure that you're actually converging to where you want to. That's all I got. Have a good weekend.